Welcome back to Book Club. Actually, Book Club number 10, Into Double Digits. And this time I want to go through a little bit of nuclear science and engineering. Why? So I've always had an interest in advanced propulsion concepts. In fact, some of the work I'm doing right now at my Navy Reserve capacity attached to DIU is some nuclear engineering propulsion stuff. In fact, I'm taking my JPME courses right now through the Area University, and I'm right on kind of nuclear space propulsion as part of my thesis work. So this is actually a great excuse as I'm sort of finishing up that thesis now to kind of go through and make sure I've got the right fundamentals for nuclear engineering. So I'm starting to get a lot out of this teaching stuff. I've always found teaching as a way to sort of lock information into my head. And I hope you get some stuff out of this as well. So just like all book clubs, really the whole idea here is they're great books. You don't have to register for a class. You can actually get a book. The idea here is just in my lectures, I'll cover the kind of the high points, and then if you read the rest of the stuff in the book and dig in, especially things like doing homework, you'll really have a full mastery of this subject. So chapters 1 and chapters 2 here is really just start with the basics, and so I'm just going to kind of do a little bit of framing in this first episode, and just a couple things on units. There are some weird units when we start getting down into the nuclear world. Okay, so just to sort of be complete, okay, on the unit front, there's things called an electron volt, and that is literally just an energy. If you have a charge and a 1 volt drop, and you have electric charge, it's an energy measurement, right? I've talked about this before in other book clubs. The point of units is for communication. It does nobody any good to tell me how many football fields it is between here and Mars. I just don't understand, right? Or here to the moon, right? In fact, I would rather talk about the moon being 30 Earth diameters away. That's a much more reasonable number for me in my head than this many bazillion miles. So EV it's a tiny unit of energy, but when we're talking about energies at the atomic scale, it's actually the right kind of level. Okay, an AMU. This is actually referring to carbon 12, right? As sort of the standard carbon 12 at 12 AMU. And so this is just kind of the number of protons and neutrons. You have H for Planck, and we may get into where this was derived, but this is writing it down. It's like 6.6 times 10 to the minus, I think that's a 34 joule seconds, right? Or it is 4 times 10 to the minus 15 EV. So it's a tiny unit. Okay, ultimately this does come from the fact that energy is quantized, and so this is a very small piece of energy. I mean, 10 to the minus 34 joules, very small. Okay, and so H bar, which we may see a lot, is actually just 2 pi h. That shows up a whole bunch, so we just compact it into H bar, and then a few other ones. K, Boltzmann constant. This one will show up. We'll actually talk about some of that early work in kind of radiation and where Boltzmann comes from. And let's see, 8.6 joules per Kelvin. All right. And then Avogadro's number. If you've taken chemistry before, you've seen this. 6.02 times 10 to the 23, and that's atoms per mole. Okay, so hopefully if you've had a little bit of chemistry, I'd probably say a little bit of chemistry is probably a stepping stone to get into this. If you haven't had chemistry, you're going to be pretty lost pretty quickly. And so that's kind of the basic part. Now, when we get into some of these basic building block of physics. So there's actually an important story here of building blocks, and we'll get more into the different models of the atom, but the story of science always sort of has these cycles. Okay, sometimes the cycles can be 20-year cycles, sometimes they can be 100-year cycles. In fact, I'll tell a story today of a 100-year cycle. But these 20-year cycles usually are this, like, we have a model, and one of the things I wish scientists did a better job of is talking about when things are models versus when things are, deeper, like laws or, more firmly held ideas. So a model is usually something that we observe these experiments, we observe these weird phenomena, And we have to kind of create a model of the universe that tries to help explain that. Okay, so the atom was one of these ones that had big changes in the model of the atom, where we used to think it was just this oatmeal cookie, protons and this blob, and then it turned into the Bohr, where it was electrons orbiting it, and then that didn't work, and then we turned it into the Schrodinger model, Bohr model. So there are all of these different models, and then they break, and then sometimes we actually get stuck on a model for 100 years, for lots of different reasons. So I'll get into this, but the current model that we know of from a building blocks, so we actually used to think it was just kind of protons and neutrons and things like that, but from a building block, we're now at the point now where we understand that there are quarks. There are all sorts of flavors. I'll show a picture here, a bit of the flavors of quarks. But a proton is actually made up of 3 quarks, an up, down quark, and a neutron is actually an up, down, down. And so we actually, we can smash these particles together in a particle accelerator. We can see these things coming off. And we have lifetimes, we can measure all this stuff. A lot of this stuff has been truly driven from particle accelerators, and we're always building bigger particles to get more understanding of sort of the model of the building blocks of the universe. Okay, mesons. You can actually have some interesting mesons. So here, for instance, the pion, positive pion is actually an up and then an anti-down quark. So anti is just the antimatter of it. And then leptons is the electron, which you're probably familiar with, and then its sort of heavier siblings, the muon and the tauon. Okay. In fact, there's still some models. People are a little too sure about the tauon. There's a couple models that actually would have some other ideas of the tauon. And honestly, this doesn't stop. There are still a whole bunch of things we don't know, including, like, we have this dark matter, which is, we can see its effect. We can take a look at the stars. We can see this effect of there is matter that is doing gravitational lensing of the light going around the stars. It's dark because the matter itself isn't emitting light. Most of our astronomical observations are basically all telescopes, right? So it's only based on light measurements. So dark is just like, it's not emitting light. We don't know what it is. So a couple interesting theories of what is dark matter, but we can measure it in the universe. And same thing with dark energy. And dark energy is us actually being able to measure the sort of acceleration, kind of the size and acceleration of the edges of the known universe. And then that acceleration only comes from a certain amount of energy based on our current models of the, our models of the universe, expansion of the universe, which suggests that there's this energy we're not accounting for. We don't know what it is. So, big, massive world, honestly, in the world of physics, of a whole bunch of things we don't know. So, yes, there's this idea of trust science and science knows and all that stuff. The answer is, no, science really doesn't know a whole lot of stuff still. In fact, anytime you sort of have a discipline of science really starting to more admit how much they don't know, that's usually about when you have a boom. There's a big boom right now in medical science. A lot of it is around just how much they don't know. And so there's all of these different ideas and innovation coming, really kind of stemming from that. That's pretty exciting. Okay, and then just as a reminder, we do have isotopes, and what we're going to talk about here for isotopes and the nomenclature, kind of sticking with the book. So if I said H, that's hydrogen, we would understand that has 1 proton. This is kind of back to chemistry. And so if I put a superscript up here, that is absolutely hydrogen. Okay, and the 1 up there refers to how many atomic masses. And so if I said hydrogen with 2, really hydrogen is actually the same thing as 1 proton. So this is now 1 proton and 1 neutron, and that is deuterium. And deuterium is one of the fuels in nuclear fusion, where if you smash them together, you can get helium and get a bunch of energy out. Likewise, tritium is 1 proton, 2 neutrons. Tritium, and that is actually the smashing of tritium and deuterium is actually sort of what they think, which they would call generation 1 nuclear fusion. It's actually should be the easiest to achieve. Lots of nuclear radiation coming from it, but this is a lot of where all of the fusion research is headed towards getting net power out of that smash reaction. Okay, and then something like this, where we have U, that's uranium-235, and then uranium-238. So some of the different examples. 235 being sort of the The natural one, 238, is the one that usually is considered fissile. It's the one that'll split, and so we'll hear a lot about those. Okay. And where I'm going to finish a little bit is in sort of the history of nuclear science and really the history of physics. And there are some. The word is catastrophes. The physics community has a few things they end up labeling catastrophes, which is just like, we have models that are so varying, like something is wrong, we are missing something here. They would call it a catastrophe. And so one of the earlier catastrophes was actually on radiation. Okay? Our model of radiation worked well up to a point, and that said radiation versus wavelength should keep going up, and it didn't. What we observed was something else. So actually, this is what we observed. This was the sort of the energy containing in, so this is like would be our sun. This is sort of the temperature. So there's temperature. Temperature radiates in this black body shape. And our model, we could actually get the right side of this tail, but our model kept going up. It was saying that there should be infinite in here, and that wasn't the case. And so the catastrophe here, what actually solved this, was this idea that energy is quantized. Okay? Quantized in units of h, which is back here. And so as they went, Boltzmann went and redid this math based on the fact that energy wasn't continuous, it was only in these chunks. So at some point, when you got here down to lower wavelengths, the chunks, you could finally detect the chunks. This is actually the form it takes. So that was a big save. But that was really what started this whole world of, one of the key words in quantum mechanics is quantum. It is quantum bits of energy. Okay? So that was a really big one. The splitting of the atom was a big one. If you've watched Oppenheimer, there's that big scene where it's like it shouldn't happen, and he's like, well, come look at it, we did. And then they had to rebuild their model. And then this is some of where kind of the quantum model, Bohr model of the atom. And there's also, like, we'll get into like kind of the teardrop model of the nuclear, kind of the protons and neutrons, the teardrop model. We'll get into that. Okay. I'll just list the ones that actually don't have any solutions for. Okay. Let's see, what is the next one? Standard model. Okay, I'll get to that. So a couple other ones we don't have any answers for is actually string theory, if you've heard of that. String theory is in big D-conflict, I'll just say question mark, with quantum. Okay? We can't, quantum mechanics and gravity. We actually can't figure out how to smash these two together, and string theory was sort of the leading idea, and it's been 40 years, and string theory isn't doing anything. So there's something we're missing, either in our quantum mechanics understanding or our gravity, which is really kind of special relativity, kind of the rest of physics. There's something we're missing here. Okay, let's consider a catastrophe. And the other one, I already sort of mentioned it, but it's the vacuum energy density of the universe. And these ones, I think the number is there. The two ways differ by, I think, 10 to the 129. Like it's a big, massive. If you add up what we think is the vacuum energy density from kind of quantum mechanics and quantum chromodynamics point of view, we get one number, and we add it up based on our observations in the universe, we get a very big, different, massive number. So those are sort of the current couple catastrophes we solved, and a couple catastrophes that we have absolutely no idea. We can't resolve these. So there's always these exciting times in physics when you do that. Now, one of the ones that we did resolve pretty well, and I'll actually try to list it. I think my picture might be too big, so I'll list it here. Okay, I'm going to talk about quantum mechanics, okay, in general, and I want to just highlight there are 4 pillars to quantum mechanics, and you can hear a little bit of my skepticism in some of this. I've taken quantum mechanics, I've taken graduate quantum mechanics, right? I've got half of a PhD in physics. One of these days I'll go back and finish it. But the 4 pillars of quantum mechanics, the first one is actually the energy is quantized. Okay, that's great. And we know this is true not only from some of these key experiments, but the photoelectric effect really kind of shows this for sure. All right, so we have high confidence in this one. The second one is 2 and 3 are actually observations. Okay, what we have is diffraction. If you've ever seen the two-slit experiment, we see that when we're blasting electrons, we know we do it when we blast photons, we can get interference patterns, but we see it when we blast electrons. In fact, we've actually seen it up to the point of, I think it was like a buckyball that was like 2,000 atomic units, and we still see diffraction. So we have these matter diffraction waves, which is really, really weird. Okay, and then there's an experiment. So this is, kind of this weird probability ability canceling. Okay, so very strange activity we expected with light, but we did not expect with matter. And then there's the Stern-Gerlach experiment, which you should go read about, but it's ultimately about, like, we have an apparatus that says, hey, there's something called spin within atoms. If you send a stream through a Stern-Gerlach apparatus, what they're getting is you would get some that would go up and some that would go down. Okay, up and down. And then if you took the downstream and you did the experiment again, but you did it sideways, you would get half of them that would go left, other half that would go right. And then if you took the same experiment again and you did up, down, you would have expected to get down because you took it off of the down leg. No, what you actually get back here is up and down. And so you have to have some way of handling this. And the Stern-Gerlach experiment, what the result of this model is actually this model of superposition, which is a key model that goes into, in fact, it's getting a little big, let me go, we can read it. Superposition, this is a key model that gets into things like quantum computing and a few other things. And so, anyway, this model, these two models are, the model of superposition is one way to explain it, and at least my personal opinion, this is not nearly as solid as, say, energy is quantized. Okay, and then 4, the big one that kind of comes in was the Schrödinger equation. And this is a model, I'll just say the Schrödinger model, and it solved a couple of things, but there's also a whole bunch of stuff it just doesn't solve well at all. And you have to kind of like keep trying it and modifying it and do a few things. So it's had some success, like all models do. All models have some success, and then there's a limit to where they sort of fail. But this helped us explain a way to have these waves, superposition, that kind of stuff. But it is currently failing in a few ways. I mean, even it can handle hydrogen atom, it can't really handle helium atom, and then to get past that, it gets really, really quite gnarly. And then there's things that, like the vacuum energy density or string theory. Like there's a couple things that, like, maybe what's wrong here is this model is only not quite complete. Okay, kind of my personal opinion. It's not detracting from what the Schrödinger equation does solve well, but they're like every model, even the oatmeal atom model, Rutherford's atom, had sort of ran out on the things that it could explain well. Okay, but the other things we've done well, and this is more kind of particle physics. The next diagram is actually, right, this is all of the standard model. So we've kind of smashed things at particle accelerators, and we see all of these different things. We actually have this sort of model built out of what all these building blocks are made out of, right? So there's your leptons, and then your neutrinos, your quarks, right? It's not just up-down quarks. You got charm and strength, truth and beauty, and then you have even up to the Higgs boson that we finally kind of detected. While the Higgs boson is where we think mass actually comes from. So I'm not going to get a ton into this right now. We may talk a little bit more about it later. But we have a fairly complete model. The standard model here is fairly rich, but it's almost an observational model, which is great. It's built upon observed experiments, and so very, very successful. But it still doesn't quite smash and complete up string theory, or like where does all this come from. All right. We're going to talk a lot about the chart of the nuclides as well throughout this book, and this is just along the top axis here is number of protons and then number of neutrons, and you'll see that we end up having all of these different radioactive elements which have different decay rates and things like that. So there's actually quite a lot here. Again, tons of experiments, and we've got some decent models to get in there. Some things called magic numbers we'll have to get into, but we'll be able to use this a lot to sort of kind of get through decay reactions and things like that, where nuclear energy kind of comes from, and really all of the nuclear science. Nuclear science is sort of the broader term. We're not always just interested in splitting uranium. It's sort of the broader term of all of these isotopes, and in fact, a big industry in medical isotopes. So this is, I'll try not to just be too laser focused on sort of the nuclear energy or nuclear propulsion side of things. Okay, and then I'll just leave you with Isaac Newton. Okay, Isaac Newton, for sure, one of the most brilliant scientists around. Most famous for the apple fall on my head, the model of gravity. Okay, that's one example. The model of gravity for Isaac Newton was a great model. It did not explain relativity. So actually, Einstein was the one who kind of took effect of the, speed of light is constant, and then gravity actually comes out of a curvature analysis. So anyways, the Isaac Newton model of gravity was ultimately still useful in certain regimes, and then in other regimes you have to go to the more accurate model of general relativity. Okay, so this happens all the time. But the one I want to highlight here is actually this picture. Sir Isaac Newton also had was working in optics, and sort of right at the height of his career towards his death, he believed strongly that optics was these like corpuscles, kind of like bowling balls, kind of bouncing around, and he had done an experiment kind of splitting it. And this model was wrong. Okay, this model was wrong, but he was of such prestige. I mean, he's buried in Westminster Abbey, and just, he was of such prestige that for the next 100 years, anybody who had a different model of optics, and you were going against the Sir Isaac Newton, you were diminished and laughed away and all this stuff. So there's this idea that scientists and academics are ivory tower and pure, and we have honest discussions. No, we're still people too. Okay, and the answer and the result of this one was 100 years of being wrong, until Fresnel actually was about 100 years later started showing a bunch of different stuff that really showed this was closer to diffraction and spherical things, and it was kind of a combination. And I'm forgetting the other scientist that was involved in there, but Fresnel is the one, and if you're in the world of optics, you've heard of both Fresnel and Newton. Fresnel was the one that kind of came up and really kind of cleaned this out. So just the idea of really, I want to, and this is doing the basics here. I actually want to do this very much highlight that this book and many deep physics books like this are going to really talk about the models as we know them. You as a reader, don't get too hung up on these models as truths. They are models, which means they're useful, and they always have their limit. So this would be a great book to kind of dig into. Lots of good stuff, especially if you're just an engineer. This really butts you up on the world of engineering and science, right into the world of physics, which is pretty exciting. And there's always really interesting combinations. So hope you join me. Get a copy of the book if you can, read along, and we'll see you next time.